Hi, today I'm going to start to talk about the product of inertia. Product of inertia, to calculate product of inertia, it has an equation similar to the moment of inertia, and it's going to be the Ixy is equal to integral of x y dA. So in moment of inertia, we either have the x squared or y squared this and times dA. Here we have x, y, dA. That's how we calculate the moment of inertia. Similar to moment of inertia, it has the units. Its units is gonna be the length to the power of 4 because the length x is length, y is length, dA is length squared. So it's gonna be meter square or feet square or millimeter square to meter to the power of 4, feet to the power of 4 or millimeter to the power of 4. And that's the unit it has. Um, uh, so in either way, it's a length to the power of 4. Another point about the product of inertia is that unlike the moment of inertia, which is always positive, the moment of inertia, the Ixy, it can be negative, it can be 0, or it can be positive. So because the x can be either negative or positive, y can be either negative or positive, and d is always positive. Because of that, it can be negative, 0, or positive, unlike the moment of inertia, which was always positive. Another point about a moment of inertia is that uh, if either x or y, if I would say if x or y, either of the x or y is symmetry axis, if either of them is symmetry axis, then in that case Ixy is 0. So in other word, if when you want to calculate the Ixy, if either x or y is symmetry or both of them, the symmetry axis is if that the cross section has symmetry about x or it has symmetry about y or about both of them, you don't need to do any calculation, just straightforward. It is 0, so you can say this is 0 and you don't need to do any calculation. In general, if I want to look at it how that works, and when if here, especially here when it says that it can be negative, it can be 0, it can be positive, let's assume that we have the x and y axis here. So if I have an x, y axis and I have a shape, assume like that in this area, and if I go ahead and divide that in 4 quadrants, so I divide it into the 4 and says that okay, this is the first quadrant we have, so it's going to be the first one, and then here the second one, and then here we have the third, and this quadrant is going to be the fourth. So whatever we have here from the cross section is in the first uh, fourth of the or first quadrant is the second one, third one, and this area is the fourth one. Now if I want to write it for the very first area of that, I can say that in this area that's going to be 1, I know that the x is going to be positive and y is going to be positive. Therefore Ixy for this particular area that is here between uh, in the first quadrant is going to be positive because dA is going to be positive, x is positive, y is positive, so Ixy definitely is going to be positive. For here, that's going to be the second quadrant here that we have. We know that the x is negative and y is positive. Therefore, Ixy in this quadrant is going to be negative. In the third one, what we have here, x is negative. We know that whatever x we have here is all the x is negative. The same for the y is negative. Therefore, Ixy in this quadrant is going to be positive. And here in the first quadrant here that we have, we know that the x is positive and y is negative. Therefore, ixy in this quadrant is going to be negative. And eventually what we have is that the ixy, the total ixy, is going to be adding all these four together. So it's ixy1 plus ixy2 plus ixy3 plus ixy4. So if these two that are negative are larger than these two that are positive, so it's going to be negative. If these two quadrants that are positive are larger than these two that are negative, so it's going to be positive. And if they cancel each other, so it's going to be negative. So it depends on how the positive one and the negative one here is going to be add together, how it's going to add up together. So you may have the positive ixy, you may have negative ixy, you may have the 0 ixy. The other, similar to what we have for the moment of inertia, we have the parallel axis theorem also here for the product of inertia. So what says that? The parallel axis theorem, or the method we can use, is that says that if we have, again, go ahead and say that if again, assume what, so I have an x and y axis, so that's the x and y, and then I have a cross section here. And for this cross section, assume this centroid of that cross section, and it's going to be the axis going through the centroid, x prime and y prime. It says that if I know the value of the product of inertia ixy about x prime and y prime, then from those two I can calculate the moment of the product of inertia about the x and y, similar to what we have for the moment of inertia. And it's going to say that the ixy about any x and y is going to be I about the ixy about the axis going through the center of that shape. So that's a ixy about axis goes through the centrum plus the area of the cross section and times the distance between axis between x-axis and y-axis. So it's going to be times d sub x and times d sub y. And again, remember, these are the d sub x, d sub y. These are not the dx or dy, which are the differential elements. So the d sub x. The d sub x is the distance here that we have between these two axes. So between the y and y prime, so it's going to be d sub x. And the distance between the two x-axes here is going to be d sub y. Unlike the one that we worked when we were working in the moment of inertia, this, instead of having dx dy, we had either dx square or we had dy square. So we didn't need to be worried about the sign of the dx or d sub y. But here we have to keep the sign. So remember that for the dx and for the dy, for both of them, for both dx and dy, we have to keep the sign. So if they are positive, if they are positive, they are going to be positive. If they are negative, they are going to be negative. So we have to keep the signs for dx and dy in our calculation. Now let's look at an example to see how we can calculate product of inertia. So assume this is the area we have here, and we want to calculate product of inertia for this area. So in the x-axis, assume this is 10 millimeter and the y-axis is 2000 millimeter, and it's not a scale in the x and y one by one. So if this is what we have, again similar to other cases that we do the integration, we need to define a differential element. Here a little bit, the calculation here is a little bit different from what we done before. Is that first we assign a differential element, and then we calculate the product of inertia for that element, and then when we calculate the product of inertia for that element, we integrate the product of inertia for that element to obtain the product of inertia for the entire surface. So I will show you how we'll do that. So first of all, we'll go ahead and assume a differential element. So here I will assume this is the differential element I would consider here. So, and this is going to be dx, and its centroid is, for this differential, is here. Now I will redraw this shape again. So draw the axis. So it's the x-axis and y-axis, but only I draw the differential element here. So this is a differential element. We have it here in this case. So, and we know that this is going to be dx, and this distance up to here is x. So this distance is going to be x, and this distance here is going to be y. Well, let me put it here. So also this is going to be y, and as we can see here, this top point of that element is on this curve, which is on x and y. And then if we draw its centroid, the axis going through its centroid. So if we have, this is its centroid, the axis go through its centroid, it's going to be the x prime, and then the y is going upwards, going to be y prime. Now if we want to calculate the expression, first of all, this is going to be the dA. So what we have here is going to be the dA, and the dA here is y dx. So we have the dA is equal to y dx. So because we have the dx, we have to also replace y with the x. So here, if you look at here, the y is 2x prime. So also we have this y is 2x cube. So if we put these together, I would gonna say that the dA is gonna be 2x cube dx. So this is the dA we have. Now I would write I would calculate the product of inertia for this element. Forget about this surface. Assume we want to calculate the moment of inertia for this element. If I call this the moment of inertia for that element dIxy, and based on that parallel axis method we have, is that it is equal to the product of inertia going through its centroid plus its area I call it dA, and the distance it has between the axes, so the d sub x and the d sub y. Again, this d sub x is different from this dx, so don't get confused between these two. So this is dx is the differential element, this d sub x is a distance that we use it here. So one more time, so assume this is what we have, assume only we have this rectangle here, and we want to calculate the product of inertia for that rectangle. That rectangle has a width of dx, height of y, and this is how we want to do that, to calculate the moment of inertia. So we call it, and these are just the name we call it for that. So first of all, it's a rectangle. Because it's a rectangle, it has a symmetry about the x prime and y prime. So x prime and y prime, both of them are the symmetry axes. Because of that, the moment of inertia about those axes are going to be zero. Remember it says if we calculate the moment, the product of inertia, if we calculate product of inertia about the axis that one of them or both of them is symmetry axis, then the product of inertia is going to be zero. So we don't need to do any calculation for this part because this is going to be zero, since both x and y, since both x prime and y prime are symmetry axis. Then so if we do calculation, so it's going to be 0, then plus the dA, which the dA is going to be this value here, so it's going to be 2x cubed dx. So this is the dA, and then d sub x, which is going to be the distances between the these two axes. So this will be y prime, and so this is going to be the d sub x, and d sub x is equal to x here, so you can see that, and then times d sub y, which is going to be this distance here. So this is the d sub y, and d sub y is half of the y, and using this equation here to replace that, so it's going to be half of the 2x cubed. So if we use this equation here, replace the y with so replace the y with the 2x cubed, and this is what we are gonna get. So if I replace it, the d times dx, d sub x, which is going to be x, and then d sub y, which is going to be half of 2x cubed. So this is what we are going to have. So if I write it here, so this is going to be dA, this is going to be d sub x, and this is going to be d sub y. So if I do the calculation, then I am going to have the dIxy. The product of inertia for this rectangle here would comes out as 2x to the power of 7 dx. Now to calculate the moment of inertia, the product of inertia, Ixy, I just need to integrate this value here. So I just integrate dIxy, and here dIxy is we have the dx is function of dx, so we have the integration in the x-axis. So it's going to be from 0 to 10. So it's going to be 0 to 10 because we integrate along x-axis, and then we have 2x to the power of 7 dx, and if we do the integration, it's going to come out as 250 -2 millimeter to the power of 4. So that's how we can calculate the product of inertia for any given area. Now let's look at another example, see how we can calculate product of inertia. In this example, similar to what we had for the moment of inertia, we have a composite area, which is basically the area that we can split it into the familiar shape, is that we know its properties. Here, for example, what we have here, we can go ahead and split this shape into 3 rectangle and then do the calculation for that. For that purpose, I will go ahead and redraw that again here, and then I will start to split it and do the calculation. So first of all, draw that shape. So the middle part, and then we have the bottom part of that shape, and then the x and y axis is going to be the x, and then the y axis. Now if I go ahead and split this into 3 parts and to 3 rectangles, I split them from here. So it's going to be the top part, the middle part, and the bottom part. And I will find, so first of all I said, okay, this is the centroid of these 3 parts. So the centroid of the first one, the second one, and the bottom part, the third one. So if I go ahead and call them, so the top part, I call the top part 1, the middle part is going to be 2, so this middle part is 2, so the top rectangle is 1, the middle rectangle is 2, and the bottom rectangle is going to be 3. So I divided with these 3 rectangles. So here, and then here. So the top one, middle part, and the bottom one. Now I will go ahead and find the distance between the centroid, the axis going through the centroid, and either of these x and y axis. So if here, for example, here we have, this is going to be the x prime, and it's going to be the y prime. So the axis going through the rectangle. The same here, we have this going to be the x prime, and this is going to be the y prime. And the same here, so the x prime is going to be right on top of that x, and y prime is going to be here. So these are the centroid of these 3 parts. So x prime and y prime for each of these 3. So these are the centroids. Now we have to find the distance between these axes and the original axis for the calculation purpose. So here, the distance from here to here between the x prime for the top part and this x axis, so it's going to be d sub x for the first one, and it's going to, sorry, d sub y for the first one, and it's going to be, this distance is 60 and half of the width of this top part, so it's going to be 60 plus 5. And then the bottom part here between this x prime and the x, which is going to call it d sub y for the third one, d sub y for the third one, is going to be, this time is going to be negative because it's beneath the x-axis, so it's going to be negative 60 plus the 5. And let me make this more clear. So this x-axis, this is the x-axis here. So these are the dy1 and dy3, and the dy2, if you look at here, so you can see the dy2 is 0 because there is no distance between the x prime here and here. So I would go ahead and says I can write here d sub y for the second one is 0 because both of them are on the same. Now I will go ahead and find the distance between the y prime and y axis. So you see how much are they. So I will go ahead and choose choose another color so you can see. So here, if I start again here, so this is here is the distance between the y prime and y, and so it's going to be the dx sub 1. I'm gonna write it here, so d sub x1, and it's half of this length, so it's the 90 plus 10, half of it is going to be 50. And for here is also going to be for the bottom part, so it's going to be d sub x3, distance between y prime and y, and got half of this length, which is going to be 40. And then we have this distance here, tiny distance between the y prime here and the y axis, and it's going to be dx for the middle part, which is going to be 5 millimeters. Now that we have all the distance for all of them, we can go ahead and start to write the equation. So for the first part, I would say that for the first one, which is the top rectangle here, we have the ixy for the first one is the ixy about its centroid, the axis going through its centroid, plus its area times distance between the axes. So dx1, d sub y1. And so it is the rectangle. Because the rectangle, the x prime and y prime, both of them are the symmetry axis. So the product of inertia about the symmetry axis is going to be 0. So this part, because the x prime and y prime are symmetry, so the product of inertia about the symmetry axis is 0. And then we have the area. The area for this top part is 100 times 10. So we have 100 times 10. So that's the area. And then we have the d sub x1, which is 50. And then we have d sub y1, which is 65. And then it would comes out as 325 millimeter power of 4. For the second area, which is this middle rectangle here, we'll write that. So for the middle rectangle, we have the ix. For the second one, the middle rectangle is again similar to that. Is centroid, the product of inertia about its centroid plus its area times the distance between the axis going through the centroid by the axis we want to calculate the product of inertia about them. Again, this is the rectangle, so the moment of inertia about the axis going through its centroid is 0 because those are the symmetry axis. The area of that is going to be 10 times 120, so it's the 10, and the height of that is 120. And then if you look at the dx is 5, and then the dy. For this one, the distance between the x prime and x is 0. So it would come that equal to become 0. And then for the third one is again the similar, so it's going to be xy for the third one. It's going to be the product of inertia about its axis going its centroid plus the area, its area times the distance between those axes. Again, because the same here, the x prime, y prime for the third one are the symmetry axis, so the product of inertia is going to be 0. Its area is here is, if you look at here, is the 80 times 10, 80 times 10, and the d sub x for the third one, this is going to be 40, and d sub y for the third one is going to be negative 65. So remember, we have to keep the sign of those distances because it's beneath the x-axis, so it's going to be negative. So it's going to be negative 208 and then eventually the product of inertia ixy, you just add these three together, so ixy1 plus ixy2 plus ixy3. If you add all them together, so it's going to be 117, 1, 2. So that's how we can calculate the product of inertia if we have a composite area.